Hi, I'm Junhyeok Jang from KAIST. Today, I'd like to introduce my work, Platform-Agnostic, Lightweight Deep Learning for Garbage Collection Scheduling in SSDs. Garbage collection, an internal task that reclaims free block, is a well-known performance bottleneck on modern SSDs. Furthermore, as the NAND flash density, including the number of pages per block, keeps increasing, it is expected that GC overhead becomes more significant. To address this issue, prior works have tried to perform GC in user idle, so the GC latency can be hidden from the user. However, the problem of predicting how long will be the user idle remains unsolved. Typical approach for predicting user idle time is using threshold-based rule. This rule relies on an already simplified assumption that storage will not be used in the future once user does not access storage for a while. Based on this assumption, they schedule GC when no IO request is given for a certain amount of time. However, we observed that such an assumption does not match with real workloads as shown in the histogram below. Therefore, the rule-based methods fail to accurately predict the future request arrival, which leads to poor scheduling that exposes GC-induced delay to the user. To address this issue, we propose GC Tutor, a DNN-based GC scheduler that can precisely predict future request arrivals and schedule GC in user-invisible time. Also, GC Tutor can keep consistent accuracy even on workloads the SSD has never seen by employing a lightweight online learning mechanism. Specifically, our DNN model takes recent IO patterns as input and predicts the idle time between the last request arrival and the next request arrival in a classification form. However, we observed that DNN model with fixed parameters failed to predict workloads which the model did not learn while training. The below figure shows the accuracy of fixed DNN model on such unseen workloads. We can see that accuracy of model largely varies, and the model exhibits accuracy of less than 30% on proxy server workload. To address this problem, we introduced online model training to capture workload dynamics. However, training DNN model online is generally considered infeasible, since it usually takes more than a few hours. To make online learning feasible, we designed a lightweight online learning mechanism that leverages MetaLearning. Unlike naive online learning that learns the model parameter from scratch, our MetaLearning-based mechanism employs additional offline learning staff for rapid adaptation afterward. Our real workload-based evaluation shows that GC Tutor successfully predicts the idle time. The left figure shows the accuracy of idle time prediction of GC Tutor and fixed DNN model on various workloads. As you can see from the figure, GC Tutor always achieves better accuracy on trained workload than the fixed DNN model. Also, GC Tutor exhibits significantly higher accuracy on unseen workloads, especially on proxy and SDG workload. This is because proxy and SDG have very different idle time distribution compared to trained workloads, such that the fixed model failed to predict the idle time. As a result, GC Tutor reduced the GC-induced delay by 82.4% on average compared to rule-based GC scheduler. To sum up, our GC Tutor accurately predicts future request arrival from recent request history by using DNN model. Our model can adapt to current workload through lightweight online learning based on MetaLearning technique. By leveraging the predicted idle time, Flash4American schedule GC in a user-invisible way. Thank you.